y te hago con los pulgares.
¿Tú estás encendido?
Sí.
Good afternoon. Today our speaker is Gonzalo Manzano. He has been already with us for a long time, but in any case it's his first seminar, so I will just give a brief introduction. So Gonzalo joined us in 2011 and stayed with us for a period in which he also worked to his final work for the master, and he got finally the master at the Universidad Complutense de Madrid, so with an external realized here. He was working in quantum synchronization with Fernando and myself here at the institute, and also with other collaborators on the subjects. And then in 2012 he started with an FPI fellowships at the Universidad Complutense de Madrid under the supervision of Juan Maria Parrondo, and I joined. I'm also co-supervising this thesis. So the work he started to do with Juan Maria, he moved from synchronization. Sorry?
Juan Manuel.
Juan Manuel. Juanma.
This Juan Manuel.
I always say Juanma. So he started to work with Juanma in dynamics, and the subject he is presenting today is related to a couple of works that he has been realizing in the last year or so.
So thank you, Roberta. Thank you, everybody, to be here this afternoon. The title of my talk is Two Approaches to Quantum Thermodynamics, Small Thermal Machines, and Fluctuation Theorems. I have worked in those topics with Sandro Popescu and Ralph Silva at the University of Bristol. Also with Jordan Horowitz from the University of Massachusetts, and with Palma Parrondo in the Universidad Complutense de Madrid. So let me begin by considering a small system. I have in mind a single particle which is trapped in an harmonic potential, and it is going to interact with a surrounding environment which is at temperature T. The surrounding environment may be, for instance, air. So this particle is going to collide with the molecules of air and performing Brownian motion. It is going to equilibrate with the surroundings. Yes, we used to think in thermodynamics for very much larger systems. It had been realized by stochastic thermodynamics that it makes sense to take about thermodynamical quantities such as work, heat, or entropy, also in such small systems. In those cases, the thermodynamical quantities are no longer being defined by single numbers, but by stochastic variables, which can take a number of different values and which have related probability distributions. Stochastic thermodynamics, in fact, using this approach, have made quite general results, quite general predictions about the thermodynamics in such small systems. In fact, they have been successfully extend some thermodynamic notions to non-equilibrium situations. In this case, all the stochasticity is going to be given by thermal fluctuations, so fluctuations coming from the environment. But one maybe is interested also in systems which are fully quantum. So in that case, we have to consider, in addition to the thermal fluctuation, the quantum fluctuations, coming from the fact that the observables are no longer numbers, but operators, which again can take different values. Furthermore, there are a number of phenomena which have no classical counterpart, such as coherence, entanglement, or squeezing, that may be present in our systems. So in such situations, we need to go beyond the framework of stochastic thermodynamics and try to understand and describe the thermodynamic quantities and notions in the quantum regime. some systems in which these approaches have to be made are, for instance, mesoscopic electronic systems or nanomechanical oscillators, or also cold trap ions. When considering quantum thermodynamics, a lot of questions arises. Some of them are here. For instance, how heat and work are defined at the quantum level, how are they affected by measurement back action, if can quantum correlations modify standard thermodynamic laws, what's about Landauer's principle and Maxwell's demon in the quantum regime, what is the smallest possible heat engine and refrigerator, or if can novel quantum environments be used to improve efficiencies. So some of these questions have been partially answered, others remain open today. In today's talk, I'm going to focus on two different but related topics about quantum thermodynamics. In the first part of the talk, I'm going to...
I don't understand the question. Can quantum correlations modify standard thermodynamic laws?
Yeah. If
But, I mean, thermodynamics, I assume, is true. And systems are quantum.
yeah, but the form can
What do you
change.
mean?
Deviation.
The form of the thermodynamic laws can change due to the presence of correlation. For instance, there are some studies that realize that if you have initial entanglement, then you can obtain a flux of heat from a hot body to from a cold body to a hot body instead of the inverse transition, which is one aspect from standard thermodynamical laws.
You mean standard thermodynamic laws do not apply to quantum systems?
In some sense, but they have to be generalized too.
Do not apply to small systems to complete that.
Then why do you say quantum and not small?
Because this is a part of a small system which are described by quantum mechanics.
I always get confused. You see, that type of statement seems to imply that thermodynamics is not correct for quantum systems, which is absurd.
Well, it is correct, but the standard form may be changed. This is the point.
But not for quantum systems.
So is it for quantum or for small? Is it because it's small or because it's quantum? You see it's the same in any
No,
case.
I think it's both in any case. It's small, of course, it's variation of the small system, but the presence of quantum correlations cannot be embedded in a classical description in any case. You cannot describe entanglement with the classical statistical physics and classical thermodynamics. Where do you put it?
Well, in any case,
It's a matter of words. It's always,
no, but the quantum correlations are important.
Not in the sense that he's using the word
Yeah,
quantum system.
this is a fight that I've had since I teach statistical mechanics. Statistical mechanics is based on quantum systems and the specific heat, and you cannot explain the deviations from the partition of the specific heat if you don't use quantum mechanics.
But that's another
So,
quantum mechanics.
so thermodynamics is well established and it applies to quantum systems.
Yes,
And-
but there are two kinds of quantum mechanics.
Okay.
The one of the 20th century, which is the one that you say, that apply to big systems and statistical physics, and then the novel one, which is the one of the small system, which is
Okay,
the
but the
quantum
novel
mechanics,
is
but
big
different.
small, not big quantum.
I think
It's
it's
both
I think what
both
we're saying
small and
is
quantum.
both small and quantum,
Yeah.
not only small.
Yeah.
So small and quantum,
And not only quantum.
not only.
Okay.
And if it's small, there are also classical small systems
That do not-
that deviate from
From a
traditional thermodynamics.
From the thermodynamic
I
unit.
agree.
I mean, I'm sorry if I am big on that. There are these type of sentences that say, no, quantum is different.
But the small quantum can deviate in a different way than just small classical.
Yeah, but that should be the point to stress, because otherwise it seems that, well, thermodynamics is something, oh, now we come quantum.
No, but here the point
You
is-
cannot explain classical statistical physics. Such a thing is such a thing does not exist. classical statistical physics does not exist.
Yeah.
There is an H bar.
But there is nothing about entanglement in the things you're speaking about.
Okay, but quantum is much more than entanglement.
Yes, but
If there is H bar, it is quantum. Eh? If there is an H bar, it is quantum.
and the secret is known.
Oh, I'm sorry. Don't worry. So I'm going to talk about these two topics. The first one, which is small thermal machines. I'm going to present a model of self-contained thermal machines, which has been introduced by Sandu Popescu, Rohan Linden, and collaborators in the University of Bristol. I'm going to review this model, and I'm going to discuss the efficiency on these small thermal machines, and discuss also the second law. And finally, I'm going to present other possible models in which we are working on now. And in the second part of the talk, I'm going to talk about fluctuation theorems. I'm going to start by introducing the fluctuation theorem for classical systems. Then I'm going to talk about the quantum generalizations. And finally, I'm going to present fluctuation theorem for quantum math, which we have recently derived. So to motivate the study of heat engines and thermal machines, we can come back to the beginning of the 19th century, in the Industrial Revolution, where the steam engine was introduced and soon spread over all Europe. In that context, Sadi Carnot, who was French military engineer, performed one of the first abstract analysis of heat engines. He considered a basic model consisting in two thermal baths with different temperatures, and he used a machine which acts cyclically between these two temperatures and transform some part of the heat flowing from the hot to the cold bath in useful work. So the work is going to be some part of the heat entering from the hot bath. One of the fundamental points of Sadi Carnot was that the work that we can extract from temperatures has a fundamental limit, which is a limit which not rely in the details of the construction of the machine, but only in the different temperatures we can access. The findings of Carnot, Carnot analyzing these models with the caloric theory of heat, which is incompatible with the energy conservation or thermodynamics. But their successors, like Emil Clapeyron, William Thomson, and Rudolf Clausius, extended their analysis in other terms, and they obtained the maximum efficiency of such a thermal machine, which is this famous expression here, which is known as the Carnot efficiency. And they also established the second law of thermodynamics, which in this situation can be written in this way, as this inequality. And in the reversible regime, we may obtain here an equality, and then we can reach this maximum efficiency. The reversible limit is related with an extreme slowness. We can consider all the parts of our machine to be always in equilibrium when the heat is transformed into work. So now we can simulate the Carnot and other workers and analyze the thermal machines at the quantum scale. The model I am going to introduce has been put forward by those people in a series of papers. The two main characteristics are that it is a small model composed by few qubits. This model is composed by 2 qubits, and that it is self-contained, so no external sources of work are allowed. So what we need to construct this model to heat baths with different temperatures. I'm going to refer these temperatures as the hot temperature and the cold temperature. Two qubits with different energy level separation, EH and EC. I'm going to refer this to the hot qubit and this to the cold qubit. Here we can see the Hamiltonians, which this is the excited state of the hot qubit in this case. And these two qubits are going to be in contact with the thermal bath and are going to act as filters because they are going to select some energy level of the bath equal to the energy level separation. Finally, we need an storage system which is going to be described by an energy level separation ES, and it's going to be the system in which we want to store the work in the case of a heat engine, but it can be also a body which we want to cool in the case of right. And I am going to consider two cases. It can be, for instance, an n-level system or an unbounded system. Finally, three-body interaction is needed in order to let exchange energy, these three bodies, which are going to be given by an interaction Hamiltonian HI. So we can begin by performing an static analysis.
Sorry, how many levels do you have in the two qubits?
How many levels?
Yeah, can you go back?
Two levels.
So there should be then a sum over EH?
Sorry, where here?
Yes, or there is a sum?
Yeah, we assume that the ground level has zero energy and the excited level has zero. So we begin with an static analysis. We consider the two qubits to be in contact with the respective thermal, but for the moment no interaction are introduced. So they are going to be in equilibrium, given by these Gibbs states. And we can now look at this two qubit system as a four-level system, in which the levels are going to be made by the combinations of ground and excited levels of the two qubits. And we can identify these two transitions here, which are going to be separated by EH, and the population of those levels are going to fulfill a Boltzmann weight at TH. And obviously these other two are going to be separated by EC, and they are going to be coupled to the closed bath, and so the energy populations fulfill this other Boltzmann weight. But we are going to be interested in these two levels in the middle. We can define these two levels as a virtual qubit. They are going to be separated by difference of the two energy level separation of the hot and the cold qubit, so EH minus EC. And we can also calculate the ratio of the population, which is this formula here. So we can define a virtual temperature for this virtual qubit, which is going to be this expression here. So here the important point is that we can obtain essentially any value for this virtual temperature by properly selecting the energy level separations and the temperatures of the two baths. Finally, we are going to put in contact the virtual qubit system, and we will let it thermalize at this virtual temperature. If we plot the virtual temperature as a function of the temperature of the hot bath, we obtain this blue line here. We have fixed the two energy level separations, and we have set also the temperature of the cold bath to be 5, for instance, which are those lines here. We have also pointed the temperature of the hot bath to be this dotted line. And then we can see that this virtual temperature can have three different regimes. in one, this Victor temperature is going to be lower than the two temperatures of the bath, so we can use it to construct a fridge. In this other case, the virtual temperature is going to be greater than the two temperatures, so we can use it to construct a heat pump. And in this other regime, it's going to be negative, and this is the regime in which we can obtain a heat engine, as we will see. The three-body interaction that we use is given by this interaction Hamiltonian. It consists in two terms. The two conditions we need are the first, that it is weak. So this coupling constant is going to be much smaller than the energy level separation of the three bodies. And we need also energy preservation for this interaction Hamiltonian. So we have this condition here. And by analyzing the two terms, we see that this first term is related with the jumps down in the hot qubit, which are linked with a jump up in the cold qubit and jumps up in the storage system, and the opposite transition in which the hot qubit jumps up and the storage system and the cold qubit jumps down. In terms of the virtual qubits, it is very easy to see, and it is seen the virtual qubit jumps down and the storage system jumps up and vice versa. So we have these two transitions, so if we want to store energy in this system, we need to bias these two transitions. So we need to be the less transition more probables, and this can be done by fulfilling this condition, which is equivalent to the orbital temperature to be negative. In the other case, if we have the opposite, we obtain that the right transitions are more probable. We can now perform chemical analysis. For doing so, we consider a master equation, which has a Hamiltonian term and two dissipators, which model the interaction of the qubits with the bath. Here, this Hamiltonian is the sum of the hot qubit Hamiltonian, cold qubit Hamiltonian, and the storage system Hamiltonian. And for the dissipators, we are going to consider this expression here. And we need to assume with coupling with the baths. So these constants are also smaller than the energy levels of the qubits. And we need that the coupling constant of the interaction term divided by the coupling constant to the path remains constant. In such case, we can neglect all the terms in which we obtain a product of the two couplings, and this master equation is consistent in this case. We are going to be interested in the heat currents and in the power. The hot currents can be defined as the heat entering from the hot bath to the hot qubit, which is given by this expression. The cold current is going to be the energy outside in the cold qubit and going to the cold bath, and we have here a minus sign. And finally, the power is the energy per unit time, which is stored in the storage system. We also maybe interested in the energy spread in the. Yes?
The form of the dissipator, does it assume that every qubit is in equilibrium with its own bath?
This is what assumes is that with certain probability, the total density matrix of the three bodies goes to this expression. So one the corresponding qubit in equilibrium, and the other part, the value that
the dissipation is proportional to the distance to equilibrium and so on. Is this the assumption?
Yeah, in some sense. So for the n-level systems, we obtain one-shot engine. So it is an engine which can store work from the initial to the stationary state. because all the fluxes stopped in the stationary state. It can be obtained by solving this equation here, and we obtain a product state in which the two qubits are in their respective equilibrium states with their paths, and the storage system is going to be given by a Gibbs state at temperature, at the virtual temperature. So as long as this virtual temperature can be negative, we obtain an inverted Boltzmann distribution in which the higher energy levels are more populated than the lower ones. Here we can also see a first feature of this virtual temperature. As long as it approaches to 0 from negative values, the inversion here is higher. In the case of an unbounded system, we have not a steady state, a fixed steady state, but we obtain a regime in which we obtain stationary fluxes, which are given by these expressions here, and we obtain a engine functioning in this steady dynamics. Here all the three fluxes are proportional to the three different bodies, energies. Energy level separation, sorry. Alpha is a constant, and we have here this guy, which is the bias between the ground and excited probability of the virtual qubit. So when we have a negative virtual temperature, this is going to be positive, and we're going to obtain positive power entering the storage system. We can now calculate the quantum efficiency for these small thermal machines. This efficiency is going to be given by the work divided by the from the hot bath. And finally we obtain this expression here where eta Carnot is the Carnot efficiency. And we can obtain this formula by noticing that in this machine, the ratios of all fluxes perfectly match the energy level separations of the different bodies. So here the heat entering from the hot bath divided by the heat outside to the cold bath are EH divided by minus EC and so on. This is due to the fact that there is only one available way to interchange energy. So, for instance, by looking here at this picture, we see that the hot current only interacts with the hot qubit, which have only this available transition. So finally, we have that the Carnot efficiency can be reached when the virtual temperature tends to minus infinity. And in this case, we obtain a reversible behavior, and the probabilities in the interaction Hamiltonian becomes equal in this case. So the left and the right transition becomes exactly the same quantity. If we plot the efficiency in terms of the modulus of the virtual temperature, we obtain that the efficiency increase when this tends to higher values and approaching the Carnot efficiency. But in this case, if we plot also the stationary power entering the storage system, we see that this goes to 0, which is a well-known fact about the power in the Carnot limit, because the power is the energy divided per time, and the reversible behavior of the Carnot limit means that the height are changing extremely slowly, so the power is going to be 0 in this limit. We can also perform a second law analysis. This is we can write the second law by this inequality here. Here delta S is the von Neumann entropy change of these three bodies. And by analyzing it, we see that the only contribution the volume and entropy change of the storage system, because this is initially and finally in equilibrium, this is also initially and finally equilibrium, and the correlations are 0 initially and also finally. So we obtain here the work divided by the virtual temperature. So we obtain this formula here, and we know that when we use our condition of the ratios of the fluxes, to obtain an equality here. So in this case, we have that this guy is going to be always greater or equal than this, which is the same as for classical heat engines, and for Carnot conditions, we obtain an equality here. Similar analysis can be done in the case of the unbounded system. In this case, we obtain the power and the fluxes, and also in the in the limits of virtual temperature going to minus infinity, we obtain the reversible behavior here. So the modulus of this virtual temperature are going also to characterize the degree of reversibility in those. Finally, we are now working in different models of thermal machines. The idea is to change the transition which is coupled to the paths. In this model here, we maintain, for instance, the coupling of the cold qubit to the cold bath, but we change the hot bath, which is now coupled to this large transition here. In this other case, we maintain the hot bath to be coupled to the hot qubit, but now the cold bath is coupled to the larger transition. In both cases, we obtain different expressions for the virtual temperature. In this case, we can improve the values of the virtual temperature for the same selection of parameters, but at the cost of having less efficiency. But in this other case, we obtain the same efficiency, and we can improve the values of the virtual temperature. It can be seen in this plot here, which we again plot the virtual temperature against the temperature of the hot bath. And we see that in all the regimes, all three regimes of the machine, we obtain better values. For instance, here we obtain a lower temperature when the machine acts as a fridge. Here we obtain greater values when it's a heat pump, and here we obtain virtual temperatures which are closer to 0, so they can obtain a greater inversion in the storage system for the case of heat engine. So we have seen this model of self-contained thermal machines. We have seen that with this we can construct a one-shot engine and a steady engine. We have analyzed the efficiency and seen that the Carnot efficiency can be reached by design, and that the virtual temperature is related with the irreversibility in the model. And finally, we have seen that these models can be improved. Now I'm going to talk about fluctuation theorems. Let me start by defining what fluctuation theorems are. Sorry?
Before you move on, so you're neglecting somehow quantum fluctuation, right?
Yes, here they're not playing any role. So we have
because the population somehow is given by Boltzmann factors. So there is no H bar, as Max said.
Well, here the storage system is going to fluctuate. So the energy is going to go up and down, but the mean energy, but we have a mean energy stored in the storage system. But the heat.
Yeah, but the qubits, they have. I mean, the population of the qubit levels, they are just given by some temperature, right?
Yeah.
They are not broadened, let's say.
But we can't always define a temperature for qubits.
I mean, for low enough temperatures, I would say that quantum fluctuations would start already. then your theory will break down.
Mm,
For temperatures of the order of H over the lifetime.
I think that this is general because it takes into account any temperature. In fact, the virtual temperature here can be very, very near to zero.
Okay, maybe then discussion.
So what fluctuation theorems are? Fluctuation theorems are exact and universal statements concerning the probability of thermodynamic events, like performing work, dissipating heat, or producing entropy, in systems subjected to fluctuations and which can be arbitrarily out of equilibrium. Probably the most famous fluctuation theorem is the Jarzynski and Crookes fluctuation theorems. There are these expressions here. This is the Jarzynski equality or integral work fluctuation theorem. And this is the fluctuation theorem put forward by Crookes. Jarzynski, in one of their reviews, uses an example, which I'm going to repeat here, in order to explain the meaning of the fluctuation theorem. He considered an RNA strand which is attached to two microspheres. One of them is going to be fixed by a micropipette, and the other is going to be trapped in a laser trap, which is movable, and so we can perform work on the RNA strand by moving the main position of the laser trap. And all this system is going to be immersed in an solution, which is going to be a source of stochasticity. So the work that we can perform here is going to be a stochastic variable with a probability distribution like those here. By varying the external the external parameters from a point to the other, we perform irreversible work on the system. If we start with this system in equilibrium and we move the control parameter, we will perform some specific work, and then we can let the system thermalize again. So we stop the control parameters, the system thermalizes with the aqueous solution. And then we can perform the reverse protocol, in which we are going to go from the control parameter at position B to the control parameter at position A, and then perform or obtain some different amount of work. So the fluctuation theorems tell us that the relation between the forward probability of performing work and the backward or reverse probability of minus that work, so obtaining that work, is going to be related by this exponential here. This quantity, in fact, is the quantity appearing in the second law inequality for this case, which is called the dissipated work, which is the work done on the top of the free energy chains of the two equilibrium states. So this relation with the second law of thermodynamics can be better seen in the entropy production fluctuation theorem put forward by Seifert. The entropy production of a system coupled to different thermal baths can be written in this way here, where this is the Shannon entropy change, and this is the heat flowing from each environment. And Seifert obtained a expression for the entropy in the stochastic as a stochastic variable, which is given by minus the log of the probability of being at some position at some time t, and he used these formulas to obtain an integral fluctuation theorem and also on the Tyler fluctuation theorem for the entropy production. Here we can see that the probability to obtain, to decrease the entropy, a quantity minus delta S, is less probable than increasing it, and the difference of these two probabilities are going to be given by this exponential factor. So the entropy event, the events which augment the entropy are more likely than the events that decrease it. So it is like a manifestation of the second law of thermodynamics. Other relevant fluctuation theorems have been also derived. For instance, some which talk about out of equilibrium steady states, such as the one obtained by Maximilian Esposito and Christian van der Broek, which obtain a fluctuation theorem for two quantities. So they have like a split of the second law in two terms, and they obtain fluctuation theorem for both terms. Another interesting case is the information processing fluctuation theorem derived by Sagawa and Ueda. They obtain a fluctuation theorem for the stochastic correspondent of this quantity. But we can now go to the quantum generalizations in order to derive fluctuation theorem for quantum systems. We need to replace the probability density function for the density matrix, the Hamiltonian function for the Hamilton operator, and we furthermore need initial and final measurements in order to define our thermodynamic quantities. For instance, if we are interested in the world, by starting with some initial density matrix, we have to initially measure the Hamiltonian of the system. So we are going to obtain some energy En, and the system is going to collapse to some eigenstate. Then we can change the control parameter, and finally we have to measure again the Hamiltonian, now at the final position of the control parameters. So obtaining a different energy En and collapsing the system to a different energy eigenvalue. So here the work has to be defined as the difference between these two results of our measurements. We need also a time inversion operator to define the reversed protocols, which is an anti-unitary operator, fulfilling this equality here, and which change the states with even variables on the time reversals to adding a minus sign, and leaves change the odd variables, and the even variables are going to be changed. So using this kind of approaches, the Krug-Jarzynski fluctuation theorem has been derived, also the Krug-Jarzynski fluctuation theorem for monitoring systems, the entropy production fluctuation theorem for a system dissipating in a thermal environment, and also the adiabatic and non-adiabatic decomposition in a context of quantum jump trajectories. I am going to focus now in the fluctuation theorem for quantum maps, because this is going to be relevant if one is only interested in what is happening to the system and without caring about what is the environment or what properties it has. So I have to introduce the quantum maps. They are quantum CPTP maps, which means completely positive and trace preserving. This is the most general evolution in quantum mechanics. Each quantum CPTP map admits a Krauss decomposition, which is a decomposition like this, with these MK are positive operators, which are called usually Krauss operators, which fulfills this relation here. And we can also define a conditioned evolution when we know which of the different Krauss operators have been applied, which is given by this formula here, which it occurs with this probability. So previous results pointing out the existence of fluctuation theorems for quantum maps For instance, the Jarzynski and Krug fluctuation theory have been derived for unital maps. Unital maps are all unitary evolutions, but also measurements and pure the coherence and pure the phasing processes, but no generalization, for instance. And when the map is not unital, we instead of the Jarzynski equality, we take here a different number, which is going to be between 0 and 1. So I'm going to present now a new general theorem which goes beyond this unital case, and we have recently derived with Jordan Horowitz and Juanma Parondo. It reads like this, where sigma is a quantity which is going to play the role of an entropy production, and this is composed by two terms. The first term is going to be a boundary term, only depending in the initial states we consider in our processes. The second term is going to be related to which Krauss operator has been applied, and is also related with the invariant state transitions. So let me explain this in more detailed way. We need to start with two assumptions. The first is that our map has a positive definite invariant state. We call it pi. So as it is positive definite, we can define a non-equilibrium thermodynamic potential in this form as minus the log of the invariant state, which is going to have this spectral decomposition. And in the second place, we need that our Krauss operators are associated with only one non-equilibrium thermodynamic potential change. So if we write Krauss operators in terms of transitions between the eigenstates of the invariant state, we need that these constants here are going to be 0 when it's in the thermodynamic potential of these two guys is different from fixed value. The most simple case of this kind of maps are those here, in which we have single transitions between the eigenstates of pi, which is very similar to a classical Markov chain. But we can also consider maps in which we have a transition from one of the eigenstates to a superposition of two other eigenstates, provided they have, in this case, the same populations. So the next ingredient we need is to define a dual map in order to construct our reverse process. The dual map is going to be also a CPTP map, which allows decomposition given by these dual operators. And it's defined as the map would have the same probabilities for the outcomes in the invariant states when the dynamic. What means that? It means that if we apply twice our map over the invariant state, we're going to obtain a probability for the outcomes K1 and K2. And this has to be equal if we apply twice the dual map over the time-inverted invariant state. This definition has been put forward by Cruz in this paper here, and he derived the four operators to be on this form in order to fulfill this condition. Another property is that the inverted invariant state is the invariant state of the dual dynamics. So now, by using our second assumption, the definition of the dual Krauss operators, we obtain this relation here, which is like a generalized detailed balance condition for operators of the dual map and the original map. This is going to be the point to derive the fluctuation theorems. So we have to define now a forward process. Our forward process is going to be, we assume to start in an arbitrary initial state, which is given by this formula here. Then we are going to measure in which state it is by obtaining outcome n. Then we are going to apply our map and obtain Krauss operator k. And finally, we are going to measure in a different basis, which is in principle arbitrary, and obtain outcome n. The probability of these three events is going to be the initial probability to be in some psi n, and the unconditional probability, which is given by the usual Horn rule. Now we can define a dual process in which we start with the final state, which is given by this, and go forward by measuring here in the inverted basis, a dual Krauss operator, and this in the inverted basis also. The probability is going to be these ones. So we can obtain now the detailed fluctuation theorem by calculating the log of the forward dual probabilities. We obtain these two terms, which come from the fact that the conditional probabilities are going to be equal to e to the minus the change in the non-equilibrium thermodynamic potential from this relation here. So here sigma mn is can be seen that this is a boundary term. It only depends on the probabilities of the initial state of the forward process and the initial state of the dual process. From this equation, we can also obtain an integral fluctuation theorem and a second law-like inequality, which is this here. This theorem also applies for concatenation of maps, in which we may have different maps with different invariant states, and the only thing that changes is that instead of only one change in non-equilibrium thermodynamic potential, we have here the sum of over the chain. Some basic applications of this fluctuation theorem. I want to discuss first the boundary term. The boundary term has two usual elections. In the first one, we assume equilibrium boundaries, which means that the initial state of the forward process is in equilibrium, and the initial state of the dual process is also in equilibrium. In this case, our boundary term is going to be the difference in the energies of our system minus the difference of free energies of the two equilibrium states. This is going to be used to obtain work fluctuation theorems. And if we assume reversible boundaries, which means that the initial state of the dual process is the final state of the forward process, we obtain here these quantities, which is the stochastic volume and entropy change. So the most basic example is to recover the fluctuation theorems for unital dynamics. So we can consider a system which is externally driven, and we have measurements in the middle, and also the coherence. In this case, as the invariant state is the unity, we do this for the dual operators, and then all the changes in the thermodynamic potential are zero. So only survives the boundary term. So if we choose equilibrium boundaries, we recover the Crookes and Jasinski fluctuation theorem. And if we choose reversible boundaries, we obtain a fluctuation theorem for the one Newman entropy, obtaining that the one Newman entropy have to increase in this case. Another example is thermalization maps. In those maps are like a system in an arbitrary state, which is coupled to some thermal bath at temperature T. This is the invariant state of the map, and the cross operators are going to describe energy jumps. So the thermodynamic potential change are going to be the heat divided by the temperature, and by using reversible boundaries, we obtain a fluctuation theorem for this entropy production, and we recover the Clausius inequality. We furthermore can combine thermalization steps with unital dynamics, and then we obtain that the quantities fulfilling our fluctuation theorem are these. So we recover the Krug and Jarzynski fluctuation theorem for this extended configuration. If we also combine thermal steps of different baths, we obtain the entropy production of a system coupled to different thermal environments. Another important applications are also about Lindblad master equation. So we have seen basic properties of classical and quantum fluctuation theorems. I presented a new fluctuation theorem for quantum maps. We have seen that this fluctuation theorem extends previous results on fluctuation theorems, and we have seen two particular applications, unital dynamics and thermalization. So thank you very much for your attention.
Questions or comments?
For the small thermal machines, do you have any possible experimental implementation of those things?
I don't know well.
Because it will be funny, I mean, if I understood properly, this means that you can build a laser with heat. I mean, you heat something and then to put in this storage system a population inverter we use.
Yeah,
But,
I don't know, but I imagine that in cold trapping ion systems, which are very controllable, these things can be done.
Other questions or comments? Just a curiosity, this TD, the limit in which you are getting the Carnot efficiency, in practical terms, what was moving to a minus infinite TD?
Sorry?
The temperature of the virtual in the
What means the virtual temperature to go?
I don't remember the condition. So TB was equal to something, so it's TB going to minus infinity. What does it mean then in terms of the two hot and cold qubits?
TV going to minus infinity.
Yes.
So this means this is the Carnot point in which the
Maybe it's in terms of the hot and cold qubits, what did it mean? Which was
this is
the meaning of the condition?
yeah. This is this condition that these two guys are equal, and then the probabilities for those transitions on the left are equal to the transitions on the right. So this is like reversible behavior in which the transitions on the opposite are equally probable.
And is it correct to say that the fluctuation theorem include the previous one that you have been showing, the generalization of the Jarzynski and the Udo Seifert, the Seifert also statement that you had on the top? So the fluctuation theorem you are proposing is including that as particular cases?
Yeah, of course. Yeah. But we can consider basically whatever in this fluctuation theorem. We only need the form of the stationary state and the Krauss operators, and we can obtain a fluctuation theorem for that.
Okay. Any other comments or questions? If not, let's send Gonzalo.